Welcome to The Explainer. So, today we're diving into this really powerful way of solving problems called computational thinking. Now I know, it sounds super technical, right? But it actually comes from computer science. And what's wild is that you can apply it to, well, just about everything. So let's really break down what that means.
Okay, to get us started, let me ask you a question. What do you think connects something like map making with designing a video game and then with 3D animation for a movie? I mean, they seem like they're from completely different worlds, right? But believe it or not, they all share this one fundamental secret. And by the end of this, you're going to know exactly what that is.
So, your first guess might be, well, computers, right? Or maybe software. And look, you wouldn't be wrong, but that's only scratching the surface. The real connection, the thing that ties them all together, is so much deeper. It's not about the tools they use, it's about a specific way of thinking.
I mean, think about it. Most of us are pretty good at using computers these days. Some of us even get how they work on a deeper level. But there's this third, more fundamental skill. And it's not about using the tools at all. It's about a way of thinking that turns out to be absolutely crucial for solving problems no matter what field you're in.
Okay, so this special skill actually has a name. It's called computational thinking. And I get it, that sounds pretty technical, maybe a little intimidating, but what does it actually mean? Well, the core idea is surprisingly intuitive, I promise.
All right, so here's the key idea. Computational thinking is basically the set of mental tools you use to solve problems, but in a way that a computer could then help you execute. It's all about breaking down huge problems, finding patterns, and coming up with clear solutions. And it doesn't matter if you're in science, or art, or even history, it works everywhere.
You know, the person who really brought this idea into the spotlight, a computer scientist named Jeanette Wing, she put it perfectly. Her whole point, which you can see right here, is that this is fundamentally a human skill. This is how we think. It's not about letting computers think for us, it's about using this approach to amplify our own brain power.
Okay, that's all great in theory, right? But if it's a way of thinking, how do we actually get our hands on it? How do we learn it? Well, the good news is, researchers have broken it all down into something like a universal toolkit, a set of core principles that you can learn to spot and use absolutely anywhere.
So a computer scientist named Peter Denning came up with this really useful framework. He called it the 7 Great Principles of Computing, and his whole goal was to create a kind of shared language, a way for people in any field, not just tech, to see how these big ideas from computing could actually apply to what they do every day. So let's take a look at what these principles are.
All right, here they are, the 7 principles. You can see they cover a whole lot of ground, right? Everything from the nitty-gritty of computation to how we communicate. Now, each one of these is a huge topic on its own. So to really see how powerful this is, we're just going to zoom in on one of them today. We're going to focus on that last one, design.
So get ready, because we're about to see how this one principle, design, and specifically the 2 ideas inside it, abstraction and modularization, shows up in 3 completely different college courses. And this is where we're going to find that hidden connection we talked about right at the start.
First up, we're jumping into the world of science. We're looking at a course on Geographic Information Systems, or GIS for short. Basically, this whole field is about one big question. How do we take the real physical world, lakes, mountains, cities, and turn it into digital data that we can actually work with and analyze?
And right away, this brings us to our first big idea from the design principle, abstraction. Abstraction just means simplifying something complex to focus only on what's important for your problem. So, for instance, if you want to map a lake, you have to choose how to represent it. Are you going to use a vector model, which is basically tracing the boundary with super precise lines, or a raster model, which turns it into a grid of little squares, like pixels? Look, neither one of them is the actual lake, right? They're both simplified versions, they're abstractions. And picking the right one is a huge design decision.
Okay, let's leave geography behind for a second and jump over to the world of arts and literature into a game design course. So here, we're not trying to map the real world anymore. Now we're designing the rules that create an entirely new one.
And you guessed it, we're going to see that same tool, abstraction, at work again. Just look at these 2 games. On the surface, tic-tac-toe and this number game called 3 to 15 seem totally different. But abstraction is all about ignoring the surface, the X's and O's, the numbers, and looking for the deep structure underneath. And when you do that, you make a shocking discovery. They are the exact same game mathematically. Seeing that hidden pattern, that is computational thinking in action.
All right, for our last world, let's check out 3D animation. Now, the huge challenge here is how do you create these massive, complex, believable worlds for movies without having to model every single blade of grass or every single rock by hand? It would be impossible. Well, this is where the other half of our design principle comes in, modularization.
So here's the solution, our second key concept, modularization. How do you model an entire field of grass? Well, you don't. You focus all your energy on designing one single, perfect blade of grass. That little blade becomes your module. Then you can group it into a small clump, you tell the computer to duplicate that clump thousands of times, and then you just add a little bit of randomness. Change the size, the rotation, the color, you see? By breaking a massive problem down into one small, repeatable part, you can create incredible complexity. That's modularization.
Okay, so we've taken a quick journey through 3 really different worlds: map-making, game design, and 3D animation. Now it's time to pull it all back together and figure out what this actually means for you.
So, what was the common thread? What was that secret connection? It was the principle of design. We saw abstraction, which is all about simplifying things to find the hidden structure underneath. And we saw modularization, which is about breaking a giant problem into small, manageable, reusable chunks. That was the secret all along.
And the coolest part is, this isn't just some academic concept for college classes. Not at all. Anytime you plan a big project by breaking it down into a to-do list, guess what? That's modularization. Anytime you follow a recipe, you're using an abstraction of the super complex process of cooking. The point is, you're probably already doing this all the time. So, I'll leave you with this final question to think about. Now that you have the words for it, abstraction, modularization, design, just start looking around. Where in your job or your hobbies, or even just your daily routine, where are you already thinking like a computer scientist, maybe without even realizing it? I think the answer is going to surprise you.